Hey guys, welcome to Safi Mixed. In this video, I want to work out an exercise that will enable us to decide whether a given wave function is physically valid or not. And in order to do, I want to use this wave function and check whether this wave function is physically valid or not. And for the validity, there are different ways, but in this particular case, I would like to substitute this wave function into Schrodinger wave equation, and then from the Schrodinger wave, from the result of their substitution, we will be able to conclude whether the given wave function is physically valid or not. So what I do, I want to use this wave function and substitute it into this Schrodinger wave equation, and we see in order to put this into Schrodinger wave equation, I first need to differentiate the given wave function with respect to time once, and the given wave function with respect to position twice. So I carry first this differentiation and I write partial psi over partial t. I'm not writing this argument, but that's understood. So that this means I would need to differentiate this side, and we see that this is a constant, so I can take constant to this side and write this as partial over partial t sine of kx minus omega t. Now we know that the derivative of sine is cos, so I write this as cos of kx minus omega t, and then using the chain rule I need to differentiate this argument, and if I differentiate the argument I write it as partial t into kx minus omega t. So I can write this as a cos kx minus omega t. Since this term is independent of time, therefore the derivative of this term goes to 0, and from this term I just get minus omega, right? So I write this in the form minus omega a cos of kx minus omega t. That's the derivative of psi with respect to time. I know this result, right? Now I want to differentiate psi with respect to x. So if I do that, I can write partial psi over partial x equals, again in the same way I write it as a, and I differentiate this with respect to s, so it will give me cos of cos kx minus omega t, and then the derivative of this argument, if I take the derivative of this argument with respect to position, that is x, it would give me k, and this the derivative of this term will go to 0, so I write that directly as k, right? And I can even take that k to this position, and now okay, leave it the way it is. I want to differentiate this result once more to find partial squared psi over partial x squared. This is constant, so I take it to this position, then a is constant, and then I differentiate this with respect to position, and we know the derivative of cos is minus sine, so I write minus sine of kx minus omega t, and then again the derivative of this argument would give me 1k, so I write that k over here. That means I'm left with minus k squared. I'm taking that k to this k, so it becomes k squared a into sine of kx minus omega t, right? So I have the value of partial square psi over partial x squared. I have the value of partial psi over partial t. Therefore, I can put this value at this position and this value at this position into the Schrodinger wave equation, and that would put the Schrodinger wave equation into the form iota h bar, and then this way. And this minus, if I multiply with this minus, it will become plus, so I don't need to write that value. And let me write it the way it is. So I just put this value, minus omega a cos of kx minus omega t. That's the left side of the equation, and this left side equals minus h bar squared divided by 2m into the value of this, which is this thing, minus k squared times a into sine of k x minus omega t, and this with this, and then this term just become plus v times the wave function, so it will become a sine of kx minus omega t. From here, this minus with this minus will become plus, so I'm not going there, but I just want to put this side into a single term, and that I can do by taking this function sine kx minus omega t with this term sine ks minus omega t with this term common, and that a I'm taking to this side, so I write this as a into this minus with this minus would become plus, so I write h bar squared k squared divided by 2m, and then plus v into sine kx minus omega t. Okay, this is disastrous because the right side of the equation depends on sine function and the left side of the equation depends on cos function. So that means the left side of the equation does not agree with the right side of the equation. That means the Schrodinger wave equation disagree. Both sides of the Schrodinger wave equation disagree for this wave function, and when that's the case, when the two sides of the Schrodinger wave equation do not agree with each other, that means the given wave function is not quantum mechanically a valid wave function. However, you can check this wave function very easily by putting this into the classical wave function. If you substitute this wave function into classical wave function, you will see that this is a valid wave function for the classical wave equation, but for quantum mechanical wave equation, that is for Schrodinger wave equation, this is not a valid wave function. The reason the two sides of the Schrodinger wave equation do not agree with each other. Thanks for watching.